These are the answers to the AP Chemistry packet on topics 7.1 to 7.5. This is MCQ Practice, which means these are multiple choice questions for you to practice so you can prepare for the AP Chemistry exam. In the video description area, there is a link to the packet that accompanies this video. Now, let's take a look at our first multiple choice question. In question 1, it says equimolar amounts of chlorine and oxygen are injected into a previously evacuated rigid reaction vessel, where they react according to the equation above. The partial pressures of the gases in the reaction vessel are monitored at constant temperature and recorded in the table below. Which of the following correctly compares the rate of the forward reaction with the rate of the reverse reaction between times T2 and T3 and provides the correct justification? So this question is related to topic 7.1, Introduction to Equilibrium, and a couple of the essential knowledge statements are highlighted on this slide. When equilibrium is reached, no observable changes occur in the system. Reactants and products are simultaneously present, and the concentrations or partial pressures of all species remain constant. Graphs of concentration, partial pressure, or rate of reaction versus time for simple chemical reactions can be used to understand the establishment of chemical equilibrium. This question also relates to topic 7.2, direction of reversible reactions. If the rate of the forward reaction is greater than the rate of the reverse reaction, then there is a net conversion of reactants to products. But on the other hand, if the rate of the reverse reaction is greater than that of the forward reaction, then there is a net conversion of products to reactants. And an equilibrium state is reached when these rates are equal. So now let's go back and take a look at the data table in question 1. So we can see at the end of this data table between times T4 and T5, the partial pressures of all three substances no longer changes. So the reaction reaches a state of equilibrium at time T4, because after that point, the partial pressures of all three gases remain constant over time. But this question is focusing on the time period between T2 and T3. So between times T2 and T3, we can see that the partial pressures of the reactants, chlorine and oxygen, are decreasing, and the partial pressure of the product, Cl2O, is increasing. So therefore, there is a net conversion from reactants to products between times T2 and T3. So the rate of the forward reaction is greater than the rate of the reverse reaction. That means we can eliminate choices A and B because they say that the rate of the forward reaction is equal to the rate of the reverse reaction. So we know that's not true. The answer is either C or D because the rate of the forward reaction is greater than the rate of the reverse reaction between times T2 and T3. And so why is this? Because according to the data table, the partial pressure of the reactants decreases in that time interval, and the partial pressure of the product increases in that time interval. So the correct answer to question 1 is choice D. Now let's take a look at question 2. In question 2, it says, a pure sample of substance XY is pumped into a previously evacuated rigid container and allowed to attain the equilibrium shown above at a constant temperature. If the partial pressure of XY is equal to 0.5 atmospheres at equilibrium, what was the initial pressure of XY in the container? So this question relates to topic 7.3, reaction quotient and equilibrium constant. And as you can see on the slide, there are two different ways to write the equilibrium constant expression. You can use hard brackets, which indicate concentration, that's called Kc. You can also use the capital P for partial pressure of each substance, and that's called Kp. And the coefficients in the balanced chemical equation are used as exponents in these expressions. This question also relates to topic 7.4, calculating the equilibrium constant. And back in my video for topics 7.1 to 7.5, I mentioned something I call a rice table, where the word rice is an acronym for reaction, initial, change, and equilibrium. And if you've been answering questions or solving problems in Unit 7, then you already know that a rice table can be very useful. And then just a quick note before we go back to question 2, that when you are filling in the information in the change row of the rice table, the change in the amount of each substance in concentration or in pressure or even in moles should be proportional to the coefficients in the balanced equation. Now let's go back and take a look at question 2. We're going to go ahead and make a rice table. So there's our reaction showing that 2 moles of XY produces 1 mole of X2 and 1 mole of Y2. And it says in question 2 that a pure sample of XY is pumped into a previously evacuated rigid container. But the whole purpose of question 2 is to determine the initial pressure of XY in the container. So at the moment, we don't know what that initial pressure of XY is. Because they didn't mention anything about substances X2 and Y2, we can assume that initially the partial pressure of X2 and Y2 would be 0. It says that at equilibrium, the partial pressure of XY is equal to 0.5 atmospheres. So this is as much as we know at this point based on the given information in question 2. Now, based on the information in topic 7.3, we know how to write the Kp expression using partial pressures and then also using the coefficients in the chemical equation as exponents. So let's go ahead and write the Kp expression for this equation. So the Kp expression is going to be partial pressure of X2 times partial pressure of Y2 divided by the partial pressure of XY squared. Again, squared because there's a coefficient of 2 in the chemical equation for XY. And it says that the Kp is equal to 9, so we know the value of Kp. Now, even though at the moment we don't know the partial pressure of X2 and Y2, we can see that the coefficients are 1 and 1. And so based on the 1-to-1 mole ratio in the chemical equation, the partial pressures of X2 and Y2 should be the same at equilibrium. In other words, for every 1 mole of X2 that is produced in this equation, 1 mole of Y2 is produced. So those partial pressures should be the same at equilibrium. So I'm going to go ahead and just call them X and X at the moment. The partial pressure of XY is 0.5 at equilibrium, so that's plugged into the Kp expression. So now we have a mathematical equation we can go ahead and solve for X, which represents the partial pressure of substances X2 and Y2. So X squared is equal to 9 times 0.5 squared, and that works out to be 2.25 when you do that math on your calculator. And then the square root of 2.25 is equal to X. So 1.5 is the value that I get, and that is the partial pressure of X2. It's also the partial pressure of Y2. So now we're getting closer to figuring out the answer to question 2. Remember that we're trying to determine the initial pressure of XY in the container at the beginning of this experiment. Let's focus on the change row of the rice table. Remember that the change should be in proportion to the coefficients. And so we have coefficients of 2, 1, and 1. And we need to consider those coefficients when we are filling in the change row of this rice table. Now in this experiment, it says it's a rigid container, which means that the volume is constant. It also says constant temperature. So that means that the change in partial pressure is proportional to the change in moles. Let's go ahead and fill in the change row of this rice table. For substance X2, that's going to be plus 1.5. For substance Y2, it's also plus 1.5. And because of the 2-to-1 ratio between XY and X2, the magnitude of change for XY should be twice as much. Now, the reason why it's minus 3.0 is because the partial pressure of XY decreases over time. So now we have everything we need to answer question 2. If the partial pressure of XY is equal to 0.5 atmospheres at equilibrium, and that pressure has decreased by 3.0, that means that the initial pressure of XY in the container at the beginning of the experiment must be 3.5 atmospheres. So the correct answer to question 2 is choice D. Now let's take a look at question 3. In question 3, it says PCl5 decomposes into PCl3 and Cl2 according to the equation above. A pure sample of PCl5 is placed in a rigid evacuated container. The initial pressure of the PCl5 is 1 atmosphere. The temperature is held constant until the system reaches a state of equilibrium. Information about the initial and the equilibrium conditions of the system is listed in the table below. As the reaction progresses toward equilibrium, the rate of the forward reaction, and then we have 4 choices. So this question falls under topic 7.2, direction of reversible reactions. So we're comparing the rate of the forward reaction with the rate of the reverse reaction, knowing that eventually at equilibrium, those rates are going to be equal. So according to the initial conditions, at the start of this experiment, there is only PCl5, a reactant, in the container. Therefore, the rate of the forward reaction is greater than the rate of the reverse reaction at time 0. But then as the reaction proceeds over time, the rate of the forward reaction decreases and the rate of the reverse reaction increases. Let's go back and take a look at our 4 choices. Since we know that as the reaction proceeds over time, the rate of the forward reaction decreases, we can eliminate choices A and B. And since we know that at some point an equilibrium state is reached when the rate of the forward reaction is equal to the rate of the reverse reaction, that means that the rate of the forward reaction would never decrease all the way to 0 at equilibrium. So we can eliminate choice D. So what happens in this system is that as the reaction progresses toward equilibrium, the rate of the forward reaction decreases to become a constant non-zero rate at equilibrium. So the correct answer to question 3 is choice C. Now let's take a look at question 4. In question 4, it says, the synthesis of substance A2X4 is represented by the equation above. A 0.70 mole sample of substance AX2 is placed in a rigid 1 liter reaction vessel and allowed to reach equilibrium at a certain temperature. What is the value of the equilibrium constant, Kc, at this temperature if 0.20 mole of A2X4 is present at equilibrium? So a good strategy for solving this question is to create a rice table. Let's go ahead and do that, and let's fill in as much information into the rice table that we are given. So it does say that a 0.70 mole sample of AX2 is placed in the reaction vessel, but it doesn't mention anything about adding substance A2X4, which is the product, so we can assume that in the very beginning of the experiment, there are no moles of A2X4 present. And then it goes on to say that at equilibrium, there is a 0.20 mole sample of the product, A2X4. Now with this information, let's fill in the rest of the rice table. So the change for A2X4 would be plus 0.2. We know that there is a 2-to-1 ratio, so we're paying attention to the coefficients in the chemical equation, and that means that the magnitude of change for AX2 should be twice as much as the magnitude of change for A2X4. So the AX2 is going to decrease by 0.4 moles as the reaction proceeds. And since 0.7 minus 0.4 is 0.3, we now have completed filling in everything in the rice table. Now, while these are moles and not concentration, it does say that the volume of the reaction vessel is 1 liter. So these numbers that we have in the rice table are not only the number of moles, they're also the number of moles per liter, which represents concentration. And we are doing a Kc, so the Kc would be products over reactants using hard brackets to represent concentration. So the Kc is concentration of the product, A2X4, divided by the concentration of the reactant, AX2, squared. Again, because of that coefficient for AX2, that's why it's the concentration of AX2 squared. Now we'll go ahead and fill in our numbers for the equilibrium concentrations to solve for Kc. So it's going to be 0.2 divided by the quantity 0.3 squared. And when I do that math on my calculator, I get a value of 2.22. So that means that the correct answer to question 4 is choice D. Now let's take a look at question 5. In question 5, it says, equimolar amounts of fluorine and oxygen are placed in a previously evacuated rigid reaction vessel where they react according to the equation above. The partial pressures of the gases in the reaction vessel are monitored at constant temperature and recorded in the table below. Which of the following provides the correct information about the system at time T4? Now, as we look at the 4 answer choices here in question 5, we can see that this question deals with what's called the reaction quotient, which is Q, as well as the equilibrium constant K. So this question relates to topic 7.3, reaction quotient and equilibrium constant. Now, the reaction quotient would describe the concentrations or the partial pressures of the system at any time, and the equilibrium constant refers to the concentrations or the partial pressures when equilibrium has been achieved. So looking at the data in this table, we can see that equilibrium would be achieved when the partial pressures no longer change over time. So here is the equilibrium constant expression, Kp, for this system, and that would be from point T5 onward, where those partial pressures are no longer changing. So Kp would be partial pressure of the product, OF2, squared, because there's a coefficient of 2, divided by the partial pressure of fluorine, which is also squared because of the coefficient, and then also in the denominator of the Kp would be the partial pressure of oxygen. And since we have the equilibrium conditions at points T5 and T6, let's go ahead and plug in those values for the system at equilibrium. So it's going to be 0.7, which is the pressure of the OF2 squared, divided by 0.3, which is the pressure of the fluorine squared, and then also on the bottom would be the partial pressure of the oxygen, which is 0.65. And if we do this math, this will give us the value of Kp, the equilibrium constant. And that happens to be 8.4 when you do that math. Now let's go back to time T4, and we can calculate the value of Q, or the reaction quotient, under these conditions. It would be the partial pressure of the OF2, that's going to be 0.64 squared, divided by the partial pressure of the fluorine, which is 0.36, again also squared, and then on the bottom is also the partial pressure of oxygen, which is 0.68. So if I plug in those numbers into my calculator, I get a value for the reaction quotient of 4.6. So what I've learned is that at time T4, the value of the reaction quotient Q is 4.6. But at equilibrium, the value of the equilibrium constant is 8.4. Let's go ahead and take a look at our 4 answer choices, and we can see that since the approximate value of Qp at time T4 is 4.6, and that value is less than 8.4, or the value of Kp, the correct answer to question 5 is choice B. Now let's take a look at question 6. In question 6, it says COCl2 decomposes according to the equation above. When pure COCl2 is injected into a rigid, previously evacuated flask at 690 Kelvin, the pressure in the flask is initially 1.0 atmosphere. After the reaction reaches equilibrium at 690 Kelvin, the total pressure in the flask is 1.2 atmospheres. What is the value of the equilibrium constant, Kp, for the reaction at 690 Kelvin? So a good strategy for answering this question is to create a rice table, and we'll fill in the rice table with as much information as we can based on the given information. So it tells us that pure COCl2 was injected into a rigid, previously evacuated flask. So that means that at the very beginning, the initial pressure in the flask, which is 1 atmosphere, would be the partial pressure of the COCl2. They don't mention anything about adding the products, carbon monoxide or chlorine, so we can assume that their initial partial pressures are 0. Now, what I'm going to do is fill in the change row of the rice table in terms of an unknown variable x. And since each of the substances in the chemical equation has a coefficient of 1, that means it will be either minus x or plus x for the change. So for the reactant, COCl2, that change in partial pressure would be minus x. And then for the products, CO and Cl2, that change in partial pressure would be plus x and plus x. So in terms of the partial pressure of each gas in the flask at equilibrium, it would be, in terms of x, 1 minus x, and then x and x. And what it says in this question is that after the reaction reaches equilibrium, the total pressure in the flask is 1.2 atmospheres. And that would be the sum of the individual partial pressures of all three of these gases. So that makes an algebra equation like this. 1 minus x plus x plus x equals 1.2. And so that simplifies to 1 plus x equals 1.2, and therefore the value of x is equal to 0.2. So since 1 minus 0.2 is 0.8, that's the partial pressure of the COCl2 at equilibrium. And then for the other gases, their partial pressure values are 0.2 and 0.2. And the question says, what is the value of Kp for the reaction at 690 Kelvin? Well, now that we have the partial pressures of all three gases at equilibrium, let's just plug in these numbers into the Kp expression. So the Kp expression would be products over reactants, the partial pressure of CO times the partial pressure of Cl2 divided by the partial pressure of COCl2. So the math would be 0.2 times 0.2 divided by 0.8. So the correct answer to question 6 is 0.05, which is choice B. Now let's take a look at question 7. In question 7, it says, a chemist adds a pure sample of substance AX3 to a previously evacuated rigid reaction vessel. A decomposition reaction occurs at 500 Kelvin according to the equation above. The partial pressures of AX3, AX2, and X2 in the vessel are monitored over time as shown in the table below. At time t1, the system reaches equilibrium. So we can see in the table that would be partial pressures of AX3, AX2, and X2 of 2 atmospheres, 4 atmospheres, and 1 atmosphere respectively. So at this point, if I wanted to calculate the value of the equilibrium constant Kp for this system, then I would just plug in those partial pressures from the table into the Kp expression. And so the math would be partial pressure of AX2 squared times partial pressure of X2 divided by the partial pressure of AX3 squared, and I would get 4 squared times 1 divided by 2 squared. Now, when I do that math, I get that the Kp is 4, which actually matches the value of Kp that we were given in this question. Let's go on and consider what happens now. It says, at time T2, additional AX2 is injected into the reaction vessel, and the temperature of the reaction mixture is maintained at 500 Kelvin. Which of the following statements concerning the system at time T3 is correct? So now what we have to do is actually talk about the reaction quotient, Q, and let's focus on the data in the table for time T3. So there's my QP expression. So partial pressure of AX2 squared times partial pressure of X2 divided by the partial pressure of AX3 squared. But now I'm going to plug in the numbers in the table for time T3. That's going to be 5.06 squared times 0.84, and then divided by 2.32 squared. Now, depending on what I get on my calculator, this will allow me to decide if the correct answer to question 7 is either A, Q is less than Kp, B, Q is equal to Kp, or C, Q is greater than Kp. We don't need to know the volume of the reaction vessel to calculate the value of Qp or Kp here. So when I do this math on my calculator, I actually get a value of 4.0. So the correct answer to question 7 is choice B. The value of the reaction quotient, Qp, is equal to the value of the equilibrium constant Kp using the data from the table for the system at time t3. Now let's take a look at question 8. In question 8, it says, a solution is prepared by mixing 50 milliliters of a 1 molar solution of NaH2PO4. That's called sodium dihydrogen phosphate, with 50 milliliters of a 1 molar solution of Na2HPO4. That's called sodium hydrogen phosphate. So we prepare the solution, and on the basis of the information above, which of the following species is present in the solution at the lowest concentration? So at some point, we're going to have to consider these three equations that were given and the magnitude of the equilibrium constant K for these three equations. Now, the first thing I will mention is that sodium is present in each of these compounds. Sodium is one of those soluble snap ions. It's commonly a spectator ion when you're trying to write a net ionic equation. So there should be lots of sodium ions present in this solution. So I'm going to go ahead and eliminate choice A. Now, the correct answer is either B, C, or D. We should focus our attention on the magnitude of these equilibrium constants that were given. So in terms of topic 7.5, the magnitude of the equilibrium constant, if the K value is very large, then the reaction proceeds essentially to completion from left to right. But on the other hand, if the value of K is very small, then the reverse reaction would proceed from right to left, and the forward reaction from left to right would barely proceed at all. And so since we're looking for the species present in the solution with the lowest concentration, let's focus our attention on the equilibrium constant that has the lowest value. And that would be for the third equation. So that K value is 4.5 times 10 to the negative 13. And that's the smallest K value of the three equilibrium constants that were given. Now, because the K value is so small, it means that the reactants are favored more than the products. So the species that's present in solution with the lowest concentration would be the product of that equation that has the smallest value of K. And that makes the phosphate ion, PO43-, which is featured as a product in the equation that has the smallest value of K, that makes that species the least likely to be produced in this solution. So the correct answer to question 8 is choice D. Now let's take a look at question 9. In question 9, it says a 2 mole sample of carbon monoxide and a 2 mole sample of water are introduced into a previously evacuated 100-liter rigid container, and the temperature is held constant as the reaction represented above reaches equilibrium. Which of the following is true at equilibrium? Now, this is similar to question 8 in that we are talking about topic 7.5, the magnitude of the equilibrium constant. But if you recall, in question 8, there was a very small value of K, which indicated that the reactants were favored over the products. But now here in question 9, it's the opposite. We have a very large value of K. So this indicates that the products are much more favored at equilibrium than the reactants. Let's use this information to answer question 9. I'm going to start with choice D. We can eliminate choice D because it says that all 4 of the substances have the exact same concentration at equilibrium, and that's not true. We know that the products should have a higher concentration than the reactants because the value of K is so large. Now I'm going to go back to choice A. I'm going to eliminate choice A because it's comparing the concentration of two different reactants, which are H2O and CO. And it's also comparing the concentration of two different products, which are CO2 and H2. And that's not what's happening here. We are trying to find a choice that shows that the concentration of the products would be greater than the concentration of the reactants. Now, H2O happens to be a reactant. H2 happens to be a product. So water would not have a higher concentration than hydrogen. But the other way around is correct. So the reason why in number 9, the reason why choice C is correct is because the concentration of CO2, which is a product, should have a higher concentration at equilibrium than that of carbon monoxide, which is a reactant. Again, because K is so large, the concentration of the products should be much greater at equilibrium than the concentration of the reactants. Now let's take a look at question 10. In question 10, it says, samples of nitrogen monoxide and oxygen are introduced into a previously evacuated rigid container at 300 Kelvin. The partial pressures of the gases in the container before any reaction occurs are shown in the table above. The temperature is held constant at 300 Kelvin as the reaction represented by the equation shown below reaches equilibrium. Considering the value of Kp, which as you can see is very large, the total pressure in the reaction vessel at equilibrium is closest to, and then we have 4 choices. So we have a situation where the magnitude of K is so large, 2.4 times 10 to the 12, that this reaction proceeds essentially to completion. Let's go ahead and make a rice table, and we can fill in as much information that we can and then try to figure out what the total pressure in the reaction vessel will be at equilibrium. So our initial pressure for the reactant nitrogen monoxide is 6 atmospheres. The initial pressure of the oxygen, which is also a reactant, is 5 atmospheres. And since there's no information given about the initial partial pressure of the product, nitrogen dioxide, or NO2, we can assume that that initial partial pressure is 0. Now, in terms of the change row of the rice table, remember that that will always be in proportion to the coefficients in the balanced equation. And since our coefficients from left to right are 2, 1, and 2, then the change in terms of x will be 2, 1, and 2. So minus 2x for the first reactant, minus x for the next reactant, and then since NO2 is a product, it's going to be plus 2x. Again, 2, 1, and 2 matching the coefficients. Now, in this experiment, one of the reactants is classified as the limiting reactant, and the other reactant is classified as the excess reactant. Focus your attention on the initial partial pressure of oxygen. Also, focus your attention on the coefficients in the balanced equation. So because the ratio of coefficients is 2 to 1 for nitrogen monoxide and oxygen, if the nitrogen monoxide reacts completely with the oxygen, then a partial pressure of 10 atmospheres would be needed. Based on that 2 to 1 mole ratio, I would need an initial partial pressure for nitrogen monoxide of 10 atmospheres. But there's only 6 atmospheres of nitrogen monoxide available, so that makes nitrogen monoxide the limiting reactant because I don't have enough nitrogen monoxide to react completely with all of the oxygen. Just to remind you that the limiting reactant in a chemical reaction is the reactant that is completely consumed when the chemical reaction is completed and would determine the theoretical yield. So if I know that nitrogen monoxide is the limiting reactant, then its partial pressure will go down to essentially 0, or a very, very small number at equilibrium. And then based on that 2 to 1 ratio, the change in nitrogen monoxide is going to be twice as much as the change in oxygen. So while the partial pressure of nitrogen monoxide would decrease by 6 atmospheres, the partial pressure of oxygen would decrease by half as much, which would be 3 atmospheres. And since the nitrogen dioxide, or the NO2, the product, has the same coefficient as the nitrogen monoxide, the reactant, then its change would also be 6. Now that we know how the partial pressure of each gas is changing, we can fill in the rest of the Rice table. So at equilibrium, the partial pressure of nitrogen monoxide is going to be a very, very small number, so essentially 0. The partial pressure of oxygen would be 5 minus 3, or 2 atmospheres. And the partial pressure of the product, nitrogen dioxide, should be 6 atmospheres. So the total pressure in the reaction vessel at equilibrium would be 2 plus 6, or 8. So the correct answer to question 10 is choice B. So question 10 is the last question in this packet. I hope that you found all of these answers and explanations helpful. Thanks for watching.